So let me summarize what we just did. We made two attempts with the leg size as square root of 2. I know the covering probability would be around 68%. With the with the leg size 2 square root of 2, I know the covering probability is around 95%. If you still got some memory about what we did when we first introduced normal probability or normal random variable, we mentioned to you that there is a 1 sigma, 2 sigma, 3 sigma, 6 sigma, whatever. Okay? For any normal random variable, the probability for that realized value to be within 1 sigma is exactly 68% for any normal distribution. For 2 sigma, it's around 95%. These are just the two numbers here, okay, 68 and 95. So obviously, the reason for us to get 68 is because square root of 2 is just 1 sigma x bar, which is just 1 sigma over square root of n. Because here we are talking about simple mean, so the idea 1 sigma should be with respect to 1 sigma for the population mean, which is the the simple mean, which is the population standard deviation with over square root of n. Okay, so that's why we get 68 and 95. No surprise. So in statistics, whenever we want to do interval estimation, we will call this kind of probabilities as our confidence level. Okay, that somehow measures how confident we are with respect to our estimation. And then those intervals will be called confidence intervals. Okay, confidence intervals. In any case, we are allowed to create any interval to estimate our population parameters. Okay, we may open any interval to do estimation, but only when we can justify, only when we can measure the confidence level, we can call it a confidence interval. Okay, for a confidence interval, we must know what's the probability for that interval to hit the population mean. Okay, that's to hit the parameter we want to estimate. So that's the concept of confidence interval. So the question is just about choosing the interval length or the leg size, right? Because the center would be the population mean. The center is to be with about the sample mean. So it's not a question. Later we will do sampling. We will get numbers, and then we will get a sample mean. But what we care about is about interval length. Okay, it's about interval length. Larger confidence interval will give us higher confidence, but larger confidence interval is somehow inaccurate. So we always face a trade-off between accurate estimation and high confidence. Here, some mistakes. There's no such number 10, it's just mu. Okay? The method applies to any population mean. And we need to have this property because we just don't know where is the population mean. But we don't care. As long as we use the right way to choose the interval length, we can create our confidence. So we know when the interval size or when the leg size goes up, the confidence level will also go up, right? So what I want to do is to somehow depict the relationship between them. And we can do that with these 3 lines of our codes. I'm going to try different leg sizes, and for each leg size I want to calculate the confidence level. So that means first set up a vector z from 0.2 to 3 with 0.2 as its interval length. Okay, so this is a few vector a vector with a few numbers, and then I want to do this calculation. Well, the important thing is that I am using this p-norm function. This p-norm function allows me to calculate the left tail probability. Okay, recall that we have this normal distribution, and we are calculating the left tail probability. Multiply it by 2, we also get the right tail probability. Using 1 to minus it, we get the probability for x bar to be close enough to mu. Okay. For each z, we multiply it with the square root of 2, which in this case is the standard deviation of the sample mean. Okay, and then we may understand that when z is 1, that just means it's 1 sigma away from the sample mean. Okay, or 1 sigma away from the population mean. And in that case, it's around 1.4. Okay, it's this number, around 68%. If z is 2, then that means it's 2 sigma away from the population mean. Then 2 sigma is around here. Okay, this one, like this. Okay, so that's the idea of doing this function calculation. And once we have all those y variables, we simply need to put it into a plot function to get all these numbers. Here, z is just a unit of standard deviation, the number of standard deviations to deviate from the mean. So we multiply the, I forgot to put it, sorry, this is just square root of 2. So we multiply z with the square root, and then that's going to be the leg size, or the interval length divided by 2. Here, the important thing is that we know there is such relationship, okay? And it is an increasing one-to-one relationship. So, given any leg size, we can calculate its confidence level. Or reversely, given any confidence level, we can calculate what's the leg size we should use. Okay, so this is actually how we do this in practice. In practice, we go from a confidence level to a level size, to an interval size. Typically, we will look at the error probability. When we make an estimation, when we create a confidence interval, we want to know what's the probability for us to make a mistake. Okay, we will call that error probability as alpha. Then the confidence level would just be 1 minus alpha. In practice, people typically create confidence intervals with 3 confidence levels: 90%, 95%, or 99%. Choosing either confidence level is fine. I mean, it's common. It's common in practice. When people do statistical studies, these 3 numbers are the most popular. If we want to decide which number to choose, obviously it depends on how accurate we need. If we need to be very accurate, if we need to be conservative, then we choose 99%. We know the confidence level or confidence interval is going to be larger. If we want a small interval and we are not so sensitive about the probability of making errors, we probably choose 90%. And then obviously in practice, people prefer 95% the most because it's somewhat a balance between large interval and high confidence. Okay, so intuitively or conceptually, given any confidence level, for example, here, this is for 90%. Okay, given 90%, we are able to go right to hit the curve and find what's the interval size we need to achieve 90%. For 95%, we may do the same thing, goes to the right and hit somewhere or as the level size. How do we do the calculation? Instead of using P norm, now obviously we should use Q norm. Now, we have a normal curve, and we want to ask when will we, what's the value here so that the left tail probability is, for example, 5%. When do we use 5%? Obviously, it's when we want the probability of making no mistake is 90%. If at the center is 90%, then at two tails it's 5%. We want to ask what's the number here so that the left tail probability is 5%. Okay? We also need to enter those numbers for mean and standard deviation. Here I'm going to put 0 as the as the mean, and the square root of 2 as the standard deviation. This is the standard deviation of my sample mean, right? So the curve is for sample mean, that's obviously. But here, you probably wonder why we are putting 0. Okay, why we are putting 0 as the population, as the mean of this normal distribution. I don't want to tell you here. I think you may think about it by yourself, and you should be able to find the answer. If we want a 95% confidence interval, then here the probability to put into Q norm would be 2.5%. Okay, because it's the tail probability. If we want 99%, then at each tail we only have 0.5%. With these functions, we can do the calculation. So now we are ready to revisit our example. We have 3,000 stores, so we have 3,000 numbers. The population mean is somewhere there, but I don't know it. So I collect sample data from 7 stores, and I calculate the sample mean as 960. Okay, now the question is how may I do interval estimation with this sample? Or I should say, how may I create a confidence interval according to a certain confidence level? So up to now, we must know the population variance. Otherwise, we don't know how to do it. So to make it simple, let's assume it's some number we know. Let's assume it's sigma equals to 120. We also need either the population mean to be normal or the sample size to be large. This is how the sample mean can be a normal distribution. So here, let's assume the population is normal. Okay? Suppose we really have these two conditions. Then, given any confidence level, 90%, 95%, or 99%, we go through these steps to find an interval. First, obviously, we calculate the x bar. And then, the standard deviation of the sample mean can be calculated. Sigma is just 120, and the square root of n in this case is square root of 7. You may calculate it as around 45. In general, this particular quantity is called standard error of the sample mean. Okay, so starting from now, when we say standard error, you are expected to understand that it is the standard deviation of the sample mean. Standard error is just the standard deviation of the sample mean. Okay. So yeah, where's my pen? Standard error is just the standard deviation of the sample mean. Okay? So now we have these two numbers. Then we can calculate the lag length. The lag length should be calculated like this, or this, just as we mentioned in the previous slides. The first argument is the left tail probability. The second argument is 0. The last argument is just the standard error. And then we will get the lag length. Okay, well, please try this by yourself to see that you really get these numbers as your lag length. And then the 90% confidence interval. Would be just starting from the sample mean. We go to the right and go to the left with the lag length, and then we can get some number that is around 885 and 1030 or 35. Okay, this will be my estimation about the number of consumers entering to my stores, the average number. Okay, I'm going to say that the average number entering a store on that particular day is within 885 and 1035. Okay, that will be my estimation. And I know how good the estimation is, 90%. Okay, let's try to interpret our outcome. So let's use 95% as an example. The 95% confidence level is here, around 870 to 1050. Okay? There is an implication about this. We will claim that the true average daily consumers for all those stores is within 870 to 1050. Okay? That's my estimation, and I know we are 95% confident. Okay, or somehow it's in many situations it's quite confident. For example, in this marketing situation, I think it is good enough. So we can say that it is quite unlikely for this statement to be wrong. We don't know whether it is right or wrong. We know it may be right, may be wrong, and we never have a chance to really tell whether it is right or wrong because we can never find mu, right? But we know with probability 95% it is correct. Now, recall that there is a special discount on that day. And suppose before the discount was offered, our marketing manager has promised that the average daily consumers will be at least 850. Okay, now suppose the marketing manager has said so, then we have a very strong confidence to show that the target is really achieved. Okay, it's because with 95%, the mu is within 870 and 1050. Okay, so we are 95% confident about this. Then obviously we are 95% confident, or actually even more, that the target has been met. Okay, if the marketing manager has promised about 900, then we cannot say that. If this is 900, then we do not have a strong confidence saying that the target has been met. Okay? So that's the difference. That's the difference. When the target is 850, we are somewhat sure that the target has been met, has been achieved. Okay? So this is some way to use a confidence interval. When we have a claim, then we may use confidence interval to justify whether that claim has been met or not. Just keep in mind, it is always possible that we make a mistake. Probably we are unlucky, so that our sample is somewhat biased. So it is possible that actually mu is smaller than 850. The only thing that we can say is that we are quite confident about our result, but we can never say it is always true. So, a brief summary. Suppose we have an unknown population mean and we have a known population variance. Then we may construct confidence interval in the way we just mentioned. The confidence interval is going to center at the sample mean x bar, okay? And with the desired lag length, the confidence interval will cover mu with a predetermined probability confidence interval, confidence level. We will first choose confidence level and then find the lag size that can achieve that particular confidence level. Don't forget that we need one of the following to be true. The population must follow the normal distribution, or the sample size should be greater than or equal to 30. The first case is for the normal and the sample mean to be a normal distribution. And the second is for us to apply the central limit theorem so that the sample mean is approximately normal. Okay, that's about this part. Thank you.